Leading a startup team, whether you're delivering a sugar rush, stocking coffee, or getting a regular delivery of snacks, Office Depot has solutions that fit every startup culture, from getting those first business cards and stationery to ordering fleece pullovers with your new logo. To learn how Office Depot and the California Technology Council have partnered to bring you savings on all of these startup essentials and more, go to californiatechnology.org/member benefits. I'm Daniel Levine, and this is the Bio Report. Climate change is not often viewed as a public health threat, but it can have unexpected consequences on the spread of infectious diseases. As changing temperatures make new areas more hospitable to mosquitoes, it can raise the risk of mosquito-borne diseases such as dengue, chikungunya, and zika in areas not usually thought of as being prone to outbreaks of tropical disease. We spoke to Erin Mordecai, assistant professor of biology at Stanford University and lead author of a recent study in PLoS Neglected Tropical Diseases that looks at how climate change may affect the spread of mosquito-borne disease. We spoke to Mordecai about the study, what it means for potential infectious disease outbreaks, and how public health officials and drug makers in the developed world may need to think differently about neglected tropical diseases. Erin, thanks for joining us.
Well, thank you very much for having me.
We're going to talk about climate change, infectious disease, and your recent study in PLoS Neglected Tropical Diseases. Your study looked at the impact of temperature on the transmission of three diseases, Zika, dengue, and chikungunya. Let's begin with these diseases. By and large, listeners may be unfamiliar with these diseases as any kind of thing they'd encounter in their daily lives, but can you begin by describing what they are, where they're likely to be seen, and the availability of treatments or vaccines today?
Yeah, that's a great question. These are three viral diseases that are all transmitted by the same mosquito species. The mosquito is called Aedes aegypti and is well known as the yellow fever mosquito. So these diseases, particularly dengue, have been circulating around the tropics for a long time. So places like South and Central America, parts of Africa, and parts of Southeast Asia typically have a lot of dengue exposure. Chikungunya has emerged much more recently in just the last 3 years or so, and has recently become established in Central and South America, where we've seen really large outbreaks. And then Zika, of course, was introduced to Latin America just last year and very quickly spread throughout the Americas. And all three of these diseases are also common in Southeast Asia and in parts of Africa. They all three are called febrile illnesses because they cause fever. They can also cause severe joint pain. They have some slight differences in symptoms, but also a lot of overlap. For example, Zika tends to cause rash. And of course, you've probably heard about the fact that Zika can cause birth defects like microcephaly when mothers are infected during pregnancy. Chikungunya is probably a little less well known, but it can actually cause a transmissible long-term arthritis. So for months after someone no longer has virus in their system, they still are experiencing symptoms of severe arthritis. And then dengue causes fever and joint pains and can be particularly severe when you get exposed to dengue for the second or third time because your immune system has a heightened reaction to seeing a different serotype of the dengue virus, and that can cause a really severe reaction that can lead to even death and very severe illness. So these are really important diseases, particularly in the tropics, but they're not completely restricted to the tropics. So, for example, we've seen some cases of dengue and Zika in places like Miami, in Texas, in Hawaii even. So we have them here in North America, and we have them in parts of Southern Europe as well. So these are kind of emerging diseases that are becoming an increasing risk around the world.
And are they generally treatable?
Well, we don't have specific treatments for any of these diseases, and we also don't have specific vaccines for them. So the best treatment we can do is sort of alleviating symptoms, but we don't have cures for these diseases.
And how serious are they? What kind of a threat would they represent to someone who contracted them?
Well, they're severe diseases in the time that the person is getting them. So horrible pain. Dengue is nicknamed breakbone fever. So you can imagine something like that. You contract an illness that causes you to feel like your bones are breaking. So severe pain, they can have severe fever. Chikungunya can also cause severe joint pain. You typically recover from these diseases, so they typically don't kill people, although there are rare exceptions to that. Zika, we're learning about more recently, can have some more severe long-term consequences. For example, Zika virus can cause Guillain-Barré syndrome, which is a short-term temporary paralysis because Zika can infect nerve cells. And of course, Zika can also cause birth defects that are permanent in babies that are born to mothers that were infected during pregnancy. So those are probably the most severe consequences and the reason that we've started to really hear about these diseases in the news more recently.
We're witnessing a variety of global changes that as a consequence are changing the risk of infectious diseases throughout the world. This includes urbanization, deforestation, globalization. You looked at a different risk, climate change, and how temperature affects the transmission of these diseases, which are carried by mosquitoes. Temperature affects a range of mosquito behaviors. What does that include?
That's a really great question. And, more broadly, all of those global changes that you listed are affecting these diseases. Temperature specifically affects a lot of aspects of the mosquito life cycle. So it affects how long it takes for them to develop from their aquatic stage into their adult stage. It affects how long mosquitoes live. It affects how frequently they bite people. And then one really important thing it does is it affects the amount of time it takes from when the mosquito ingests the virus in a blood meal to when it's ready to infect the next person. So the mosquito is actually taking up virus when it bites a person, and that virus has to make its way through the midgut, so it actually has to disseminate throughout the body of the mosquito, and it eventually binds to the salivary glands, so that the next time the mosquito bites a person, it injects a little bit of saliva, and that saliva has virus in it. And that process, what's called extrinsic incubation, takes an amount of time that's dependent on temperature. So that extrinsic incubation rate tends to speed up at warmer temperatures. So we have this combination of mosquito and virus traits that all really depend on temperature. And that's what our study was really designed to address, was understanding how all of these temperature-dependent traits come together to determine transmission rates.
Zika, dengue, chikungunya have traditionally been considered tropical diseases, but we're increasingly seeing them in areas not traditionally thought of as tropical. How have they spread so far, and what areas are already hospitable to mosquitoes that carry these viruses?
That's right. We're starting to see these diseases in places that aren't traditionally considered tropical. So, for example, in North America, in the United States, during the summer, most of the United States is actually warm enough that it could theoretically sustain transmission if the mosquitoes were present. So we're starting to see the mosquitoes moving further and further north into more temperate climates. And that's in part because we're having warmer winters. So those winters aren't killing off as many mosquitoes. And the mosquitoes, these are really kind of tropical and subtropical mosquitoes, but they're able to get established further north. And then during our summer seasons when it's warm enough, we can actually start to see the potential for transmission. So we have seen some transmission in the southeastern U.S. of these diseases. And I would expect to see that risk increasing as the temperatures get warmer.
When you did your model of climate change, what did you find in terms of the potential spread of these diseases? And is there any sense as to the size of the population that may be exposed to them?
It's a great question. We do expect climate change to increase the range of people, the geographic range of people that are exposed to potential transmission, and also the seasonal amount of time that people are exposed. So maybe now climates are only suitable during a few months during the summer, but as we see warmer springs and warmer falls, we may start to see transmission seasons expanding. So not only a greater number of people at risk, but also a larger span of time where people are at risk.
Which I imagine would increase the risk of contracting the disease in those populations.
Right.
There are other models that have been made in the past. How does yours differ?
One innovation that we used in our model was the understanding from exotherm physiology, so the physiology of cold-blooded animals, is that a lot of these traits that I was talking about, like survival and development rates and reproduction rates, have a nonlinear response to temperature. So at cool temperatures, increasing temperature tends to increase the trait, but then you have an optimal temperature, and above that temperature, the trait tends to decline with further warming. So our work was really focused on trying to understand where the optimal temperatures for each of these mosquito and viral traits were. And to do that, we used data that had been collected in laboratory studies. And we used those laboratory experiments to fit model curves. So we fit a hump-shaped curve for each of these traits, describing how the trait responds to temperature. And then we incorporated those into a transmission model. And then the additional innovation of our approach was that we tried to validate that model by comparing this mechanistic prediction that was based on laboratory data with some completely independent data from the field on when and where people had been infected with cases of dengue, chikungunya, and zika. So we're trying to see if what we predict from models and laboratory data actually bears out when we look at people getting infected.
Well, what have you done to validate the model, and what do you know about the actual incidence of the disease to date and what it says about your model?
Yeah, what we showed was that the model does actually do a pretty successful job of predicting when and where we saw outbreaks. So specifically, we used data on the number of new cases each week reported at the country scale across countries in the Americas. And we got these data from the Pan American Health Organization. And we matched up these human case data with temperature data from the 10-week span leading up to that time point, because it's actually temperature a long time ago that determines your transmission risk now, because it's temperature at the time when those mosquitoes were hatching and becoming infected and biting and finally infecting people, and people are reporting cases. So we matched up human case data with environmental temperature data, and then we used our model to test whether it could accurately predict in a given week in a given country, will we see an epidemic, yes or no? Will we see local cases? And then given that we see those local cases, what's the magnitude of that epidemic? How high will incidence be, or how high will the number of new cases be? And what we found is that the model did a good job of accurately predicting both of those things, with up to 85 to 90% accuracy for both the probability of seeing an outbreak and the magnitude of that outbreak given that it happened. So we were very satisfied, given the constraints of what kind of data were available, that the model that was based on mathematics and laboratory data could actually describe a pattern of transmission in people in the field.
Why do models like this matter? How should they be used, and what do they tell us?
That's really a great question. Models like this are important for not only understanding the current distribution of disease. So when we have a new virus that's invading, like Zika, we want to know what's the potential extent of this virus? Where could we see Zika transmission? So models can be really useful for trying to address that question of when and where we might see Zika transmission. But also they can be really important for trying to predict what we might expect under future climate change. And in particular, it's easy to make the prediction that warmer temperature means more transmission. But actually what our work says is something a little bit more subtle, which is that the optimal temperature for transmission is 29 degrees Celsius, which is 84 degrees Fahrenheit. So up to that temperature, warmer temperatures mean more potential for transmission. But once we get to average temperatures that are above 84 degrees Fahrenheit, we might start to expect that future warming could actually decrease the potential for transmission of these diseases, because the climate is becoming less suitable for the mosquito and making it harder for the mosquito to transmit the virus. So our work really tries to tease apart where we expect to see climate change increasing transmission in places like the temperate zones, and then where we might expect to see climate not increasing transmission and maybe even declining the amount of transmission that's possible.
So the problem isn't climate change, but not enough of it.
Right. And you know, one big caveat that I have to give here is that climate change, compared to the lifespan of a mosquito, which is just a few weeks, climate change is occurring at a pretty slow scale. So it's very much possible that these mosquitoes and viruses could evolve and adapt to perform better under warmer temperatures. So that's why I'm careful to say that we don't necessarily expect that climate change will actually decrease the amount of transmission in these really warm places, but at the very least, we don't expect climate change to further increase transmission in these already really warm, really suitable places like the tropics.
So your study is published in the PLoS Neglected Tropical Disease Journal. The implication is that these diseases have not garnered the attention from researchers and drug developers that they warrant. As you see these diseases migrate to the developed world, do you see changes in attitude among public health agencies, researchers, or drug developers about the threat or the economic justification for pursuing treatment?
Well, I think that the Zika emergence and the research linking Zika to birth defects has really changed the story here in North America and other places that might not have been concerned with these diseases before. And the reason is that it has a major impact on tourism, on travel, on the risk, of course, of pregnant women visiting or living in places that have risk. And of course, there's even risk of Zika transmission in the southeastern United States. So because it's such a scary potential outcome of having a baby born with a birth defect as a result of an infectious disease, it's really started to grab attention of researchers and drug developers and vaccine developers. So that's really starting to change the conversation. I think previously the myth, which wasn't completely true, is that these viruses were really restricted to the tropics and that they really didn't have a major impact on people living in North America. But we're starting to see that picture changing, particularly with the fear of getting exposed during pregnancy and being exposed to birth defects.
Erin Mordecai, Assistant Professor of Biology at Stanford University. Erin, thanks so much for your time today.
Well, thanks so much for having me.
Thanks for listening. The Bio Report is a production of the Levine Media Group. To automatically download this podcast each week, subscribe to our RSS feed or through iTunes or other podcast manager. To join our mailing list, go to levinemediagroup.com. We'd love to hear from you. If you want to drop us a line or are interested in sponsoring this podcast, send an email to danny@levinemediagroup.com. Special thanks to Jonah Levine, who composed our theme music, and the Jonah Levine Collective, which performs it.